So we're starting vectors. This is the beginning of 6.1. We're actually going to spend 2 lessons on 6.1. So next Tuesday we'll also be doing 6.1. We're going to introduce vectors today. And today is going to be more about notation and operations on vectors. And then Tuesday we'll circle back and we'll look at a more visual representation of vectors, which will be more similar to those of you who've been in physics. So like your free body diagrams that you did back in physics, those we'll be looking at some things that look very similar to that. That'll be on Tuesday. Today is more kind of the mathematical nitty-gritty. What can we do with vectors mathematically? But we will be readdressing this in sort of a different way on Tuesday. So we got to define vectors, and for me the easiest way is to compare it to a scalar. So numbers that we're used to dealing with in math, most of those numbers are scalars. Scalars are numbers or measures that indicate the size of something, so length and area and weight. Vectors indicate both magnitude and direction. Do you guys remember learning about the difference between speed and velocity in science class? What was the big distinction? Between speed and velocity? Something, yeah, having a sign, and specifically having a direction. So I could say I'm traveling 70 miles per hour, that's a speed, but that's not a velocity. In order to tell you my velocity, I'd have to say I'm traveling at 70 miles per hour south. So I need to tell you what direction I'm traveling as well. So a vector is going to give you a magnitude and a direction. Some other examples of vectors that we use a lot in science would be like force. So force is different from weight. If you stand on a scale or you put something on a scale and it weighs 3 pounds, that's a weight, that's a magnitude. The force that object exerts downwards onto the scale would be the vector. And it would contain that 3 pounds and the fact that it's pointing downward. We can use vectors to define position, but vectors and position are not exactly the same thing, so we'll kind of see an example of that in a minute. What other vectors, what other examples can you think of where direction is equally important to magnitude? Pendulums. Yep, so there'd be a lot of vectors going on with different forces, velocities, and accelerations. All right. We'll see some applications pop up in our assignment on Tuesday. Torque, yes. Yep. Yes. All right, so we're going to talk notation. There are several ways to indicate a vector. So the simplest way, the way that we like to do this, because it requires the least amount of handwriting, is to name a vector using a lowercase letter. So this is important. We use lowercase letters if we're using a single letter to represent a vector. We put an arrow over the top. The arrow is, sometimes they write it as like a half arrow like mine. Sometimes you can use a full arrow if you want. You know what I mean by full arrow. See how my arrowhead, I'm not doing the whole thing. There is a technical difference between those two things. I'm not exactly sure what it is. I use the little half arrow just out of sheer laziness. It saves me milliseconds of my life every time. I don't have to draw that little extra part of my arrow there. However, typically in print, they will not put the arrows over top of the lowercase letter. The whole thing will just be bold. And oftentimes it's a slightly different font than everything else. When we copy that down onto a piece of paper, though, we'll put the arrows on it. We can also name a vector using 2 uppercase letters. Those 2 uppercase letters would represent points. Hopefully this reminds you of a particular geometric structure. What does this look like? What do we call those things? It's not a line. It's a part of a line that starts at a point and travels forever and ever and ever in one direction. Yeah, in geometry we call that a ray. And it's kind of related to that, but it's not the same as a ray either. The order is important, though. A vector starts at a point and then goes to another point. We'll see an example of that in just a moment. So if that's not entirely clear to you, that's just fine. The third way, and the most common that we'll be using, is component form. Some people call this wedge notation. It looks a lot like a point, except instead of parentheses, we use these triangular brackets. And it's related to the coordinates of a point. It's called component form because there's two components being represented, and usually it's an x and a y. Thank you. Oops. Bella is not here. Oops. Okay. All right. Does anybody have any questions, concerns so far? We're going to learn a fourth way to represent vectors in a moment, but let's go on to this. So I want to talk about the examples that are on the half sheet. Again, we're going to be utilizing this half sheet for all of our examples today. And I want it separate so that you don't have to keep flipping back to the beginning. So we've got a couple of vectors here, vector v and vector w. Again, typically in print, this would not have an arrow over top of this. This v would just be bolded instead. But anyways, here we are. You can see that vector v starts at A and terminates at B. So when we use this arrow notation, A has to come first. If I flip the B and the A, then the vector would be heading in the opposite direction. And we're going to turn this into wedge notation. So when we do this, we're going to figure out the x component and the y component of our vector. So the x component of the vector is going to be how far does the vector travel in the x direction. And if we know the coordinates, we can use the two x coordinates. We always do the terminating x coordinate minus the initial x coordinate. So I would go 4 minus 0 to get my x component. Vector v also has a y component. It is how far this vector is traveling in the y direction. And again, we can use those y coordinates, the ending y coordinate minus the initial y coordinate. So we would go 3 minus 0 to get 3. So could you guys go ahead and find components for me for vector w? Same idea. Make sure you're using the coordinates and make sure you're doing them in the order that's indicated. We always want to use the terminating coordinate minus the initial coordinate. Did I do it backwards? So this says I want the vector that starts at C and ends at D. So that's why the arrow is pointing up towards D. Now if I flipped it, it would be heading down this way instead. So C would be the initial vertex and D is the terminal vertex. Bless you. Are we feeling okay about those? Any questions about that? So we'll be setting this aside and looking at a couple quick questions, though. We can use vectors to talk about position, but they don't always represent a position. So for example, vector w is -2, 2. When you look at these points, those coordinates don't really have anything to do with the vector itself. If we want to use a vector to indicate position, then usually we want to start at the origin. So 4, 3 is the terminal point, and it always will be the terminal point if your initial point is at the origin. So oftentimes we're going to draw vectors at the origin because it just makes it a lot easier to figure out what the notation is. That means we don't have to do all the subtraction and stuff. So when we get into our visual representations on Tuesday, we'll be drawing most of our vectors at the origin. Can you guys please stop the side conversations? Thank you. All right, let's do some math with them. So some operations that we can do on vectors. So we can mix and match. We talked about what a scalar was. Remember, scalar is just a number. I'm going to cover up some of this. A scalar is just a number like the numbers that we would think about it. So the number 5 is a scalar, negative 3/5 is a scalar, pi is a scalar. You can multiply a vector times a scalar. Which we're doing here. Before we get into this, and as you guys are copying down this example, I have a big suggestion for you that's helped a lot of my students in the past. We will be getting into some pretty complicated notation further down the road with vectors. Okay, and a lot of the struggle that my students have with vectors is not so much with the math as it is with the notation and being able to read notation and understand what's being asked for. So something that can help you on that path as we head towards that is, as you are looking at a problem like this, to say out loud or say in your head what you're seeing here. I would pronounce this as 2 times vector v. So when I see that little arrow over top of something, I'm going to say in my head that's vector v. On this sheet here we have vector v and vector w. Okay, don't start referring to them as just v or w. Make sure you're putting that vector in front of it. That is going to help you out later on. Okay, so try as you're looking at a problem, before you start doing the math, speak what it's asking you to do. All right, it may seem a little bit weird, but if you do that, it's just going to get you used to the notation and the language of vectors so that you don't have to think through so much when things start getting more complicated. All right, so check it out. We're going to multiply 2 times vector v, and vector v is 4, 3, so I'm going to do 2 times 4, 3. When we multiply a scalar times a vector, we are going to get another vector. Would anybody like to guess the components of the other vector? We thinking 8, 6. If you were the inventor of vectors, is that how you would make it work? Does that kind of make sense? Yep, and that's how it works. It would be 8, 6. And where does that come from? Well, it's basically 2 times the x component and 2 times the y component, which should be a 3. I don't know why I wrote 4. So 2 times 4 and 2 times 3. So when we multiply a scalar times a vector, we just multiply that scalar times each of the components. All right, would you guys please do -3? Well, I want you to say it. Say this in your head as you're writing it down. Or out loud is fine too. -3 times the vector w. -3 times vector w. All right. I am hopeful that we ended up with a 6 and a -6. All right, so far so good. This isn't too bad, right? All right, so we can multiply a scalar times a vector. Now, we are not going to get into multiplying 2 vectors together yet. There are 2 different ways to multiply vectors to get a vector times a vector, and we'll get into those later on. And each of those is going to be its own lesson. That's where things start to get a little bit complicated. Just in case those of you who've taken physics before, have you heard of dot products and cross products before? So those are the 2 ways that we can multiply 2 vectors. Not get into that, but we will add and subtract them. So We can add and subtract two vectors. So again, I encourage you as you're writing to say in your mind, or say out loud, pronounce these things. It will make your life easier later. So in our first example here, I'm asking you to add vector v plus vector w, and I've copied down the component forms of those two vectors. I'm going to tell you that when we add two vectors, the result is another vector. If you were the one who invented vectors, how would you make this work? Anybody want to be bold and guess what were new components? You think add the components? X with X, Y with Y? That's exactly how we do it. So this would become 2, 5. That 2 I got from doing 4 plus negative 2, and the 5 came from 3 plus 2. All right, we can subtract vectors too. Give this one a try for me. Do vector v minus vector w. If I were doing this in my notes, I would probably go ahead and copy the component forms down again. When it comes to doing this on your assignments, I would recommend that you do that also. Definitely for our notes, though. So same two vectors that we were using before, 4, 3, negative 2, 2. So 4 minus negative 2 is 6. 3 minus 2 is 1. How are we feeling about adding vectors? Pretty tough? You're going to get good at it over time. Just give it some time. You'll be all right. When we're talking about scalars, okay, so when you guys remember when I say the word scalar, that's just all the other numbers that you've been dealing with throughout your mathematical careers so far, right? Okay, scalar isn't something weird or special. We just never had to use that term because there was not something else, right? So, but when we talk about scalars, I have a question for you. Is addition commutative for scalars, for numbers? Is addition commutative? Commutative means you can rearrange them. So if I do 5 plus 2, I can rearrange it and do 2 plus 5 and I get the same thing. Is addition commutative? Is subtraction commutative in scalars? No. What do you think about vectors? Do you think vectors addition is commutative? In other words, if I had rearranged this and did w plus v instead, would I still get the same results? If I had done w plus v instead, then these would have just flipped, but I'd still be doing x with x and y with y. So I'd say yes. Vector addition is commutative. What about vector subtraction? Is vector subtraction commutative? It is not. Okay. One last question. We talked about multiplying a scalar times a vector, and we talked about adding two vectors together. And I hinted to you that we will eventually be multiplying two vectors together. What about adding a scalar and a vector? Would that make sense? If I added a scalar and a vector, what do you think? No, that's not something that we do. They're two different things. They cannot interact through addition. So we can multiply a scalar and a vector, but we cannot add a scalar and a vector. All right, you guys are doing awesome. Let's keep going. Let's try, so we already talked about whether subtraction is commutative. Look at this one. Oh man, that looks like a fun problem. We got multiplication, we got subtraction. That's all the things. Yeah, label it however you like. It's your notes. I would encourage you to write this out in steps, both here in your notes and on your assignments. I am going to ask to see work for your assignments, so if all I see is an answer, because especially for this one, is all odd numbered problems, I'm going to have a hard time giving you full credit on Tuesday. So the work that I would expect to see for a problem like this would be, let's write out 4 times whatever W was, minus 5 times whatever V was. And luckily we've got that right in front of us here. W is negative 2 comma 2, and V was 4 comma 3. Do you think we should do the subtraction first or the multiplication first? Multiplication, order of operations still holds up when we're dealing with vectors. So we'll do 4 times that vector, get a new one, and then we'll do 5 times this vector and get a new one. So what would that be? Negative 8 and 8. This would be, oh, now hang on. Do we want to keep the negative with the 5, or do we want to think of it as just 5 and keep the minus separate from it? So just the 5, and we'll keep this a negative. Now, if you multiplied the negative 5 into there, what would you need to change? This would have to become a plus, okay? So if you're thinking of this as a negative 5, that's fine. You can multiply these both by negative 5, but then you would change this to a plus. I'm going to think of the 5 as separate from the minus so that I can have a minus here. 5 times 4 is 20 and 15. And then we just need to subtract those vectors, which we know how to do. Subtract the x's and subtract the y's. Negative 8 minus 20 is negative 28. 8 minus 15 is negative 7. Thank you. That was fun, wasn't it? Yeah. And most of it is. Most of your assignment is going to be pretty basic math. But the purpose of this assignment is not so much, it's to get you comfortable with that notation. So if this is basic to you, that's great. But please follow my recommendation and speak in your mind or out loud what's going on here. Get really comfortable with this notation so that when things get more complicated. So when you're doing this problem, say in your head, I'm doing 4 times vector W minus 5 times vector V. Make sure we're putting that vector in front of these. It seems weird that I'm asking you to do that, but you guys you'll see why when things get kind of messy. All right, let's talk about magnitude. So we can take the magnitude of a vector, and what we're doing when we do that is we're finding the size of the vector only. So when we take the magnitude of a vector, we are turning a vector into a scalar. When we do the magnitude of a vector, we still have the size. What we lose is we lose the direction. We'll talk about what this means visually a lot more on Tuesday, but for right now, the magnitude would be the length of this arrow. All right, so really, you're finding the hypotenuse of a right triangle, so I'm hopeful that this formula here is something that kind of looks familiar to you. Can you see where that would have come from? And if you were to forget it, like you could probably come up with it on your own. Maybe this is the Pythagorean theorem, right? But get C by itself. Yeah. So let's find the magnitude of V. All right. So I said that incorrectly. What did I mean to say? Let's find the magnitude of vector V. Now this is where this is going to become important. I want you speaking these things as you see them. This is the magnitude of vector V. The magnitude of vector V. So these vertical bars on either side, the things that look like absolute value symbols, that indicates that we're finding a magnitude. So yeah, we just need to take the square root of 4 squared plus 3 squared. And you can work out the math there, or some of you probably recognize that that's a 3, 4, 5 triangle. 16 plus 9 is 25, and the square root of 25 is 5. So the magnitude of vector v is 5. We've taken that vector v and we've turned it into a scalar. Could you please find me the magnitude of vector w? Say it in your head as you're writing it down. The magnitude of vector w. Alright, and of course we're always going to simplify radicals if we can. We will be simplifying and rationalizing a lot in this unit, and I will not be kind of showing the steps for simplifying and rationalizing. My assumption is that you know that, or that you will schedule an appointment with me to get you caught up on that at this point. So I would be happy to help you through that process. It's a skill you're definitely going to want to have, though. Right, so are we coming up with 2 root 2 for the magnitude of vector w? All right. Couple questions for you. Do you think magnitude will ever end up negative? No. Nope. Could it be 0, though? That's an interesting question. You could have 0 pounds of force applied to an object. So you're looking at it through the lens of like a physical description. I like that. We'll talk about that one in a second. Here's another fun question for you. Is if I double, I'm going to write this down and then I want you to say it out loud, outside of your mind. Is you don't have to write it down, but I want you to speak it. Let's speak it in our minds first. Wonderful. Well done. So what do you think? Is doubling the magnitude of a vector the same as finding the magnitude of twice the vector? I don't know. Yes? No? Sometimes? What do you think? What is 2 times the vector v? 8, 6. And what's the magnitude of 8, 6? And the square root of that is? So the magnitude of this vector is 10? It's another 3, 4, 5 triangle. That's twice as big as the vector or the magnitude of vector v. So I would say in this case it is. They are the same thing. That's a good question. Would it always be? Let's circle back to that question on Tuesday when we're looking at a more graphical representation, and I think the answer will be a lot clearer then. We know for a fact right now that at least sometimes doubling the vector and then finding the magnitude will give you the same result as finding the magnitude and then doubling that. We'll come back to that. This is not key for right now. Just want to kind of get you thinking about some of these weird things. So we talked about this a minute ago. Can the magnitude of a vector be 0? We have decided as a mathematical community that is an important concept, and as such, it is a special vector. So there is this thing called the 0 vector. We write the number 0 with an arrow over top of it. Would anybody like to guess what the component form of that is? 0, 0. So when we pronounce this, we're going to pronounce it as the 0 vector. This is the 0 vector. So I don't want anybody to say it out loud. I would love everybody to say this in their head, though. How would you pronounce this? This is the 0 vector. This is, don't say it out loud. Let everybody do it. This is, all right, now let's all say it out loud at the same time. 1, 2, 3, go. The magnitude of the 0 vector. Yes, awesome. You guys did awesome. And what do you think that is? How big is the 0 vector? 0. That's the definition of the 0 vector. It's all right. It happens. It happens. In fact, I don't know if I silenced mine this morning. I'm going to check real quick. Did I do it? Yep. All right. So the 0 vector is important. We'll talk more about that when we get into the graphical representations. There's some really cool things that happen with the 0 vector. And we'll also talk about it when we get to dot products and orthogonality. Ooh, it's going to be fun. But stay tuned for that. There's another special class of vector. So this is not a specific individual vector like the 0 vector, but there are certain types of vectors that we call unit vectors. Okay, now we've seen that word unit pop up quite a bit this semester. What was the context of unit? The unit thing that we dealt with for like ever was the unit circle. And what was special about the unit circle? Why did we call it the unit circle? What was special about the unit circle? 1. What was 1 in the unit circle? The radius of the unit circle is 1. That is why we call it the unit circle, because it has a radius of 1 unit. So what do you think is going to be special about unit vectors? What about 1? Well, it can't equal 1. Remember, a vector cannot equal a scalar. 1's a scalar. The magnitude equals 1? You think that's what it would be? The size of the thing equals 1? That seems reasonable. Yes. So unit vectors are vectors that have a magnitude of 1. Somebody want to be bold and give me a vector that would be a unit vector? Remember, you're going to have to give me 2 components, an x component and a y component. So, yes? 0, 1 is a unit vector. That's awesome. 1, 1 is a unit vector. No, I think that would have a magnitude bigger than 1. It would be root 2. Root 2 over 2, root 2 over 2, that is a unit vector. We said 0, 1. What's the other really? 1, 0 is 1. Hey, here's a nice connection. If I asked you to give me 16 unit vectors, would you be able to do that if you had your pink sheet in front of you? Someone give me another one. Give me one where they're both negative. Negative root 2 over 2, negative root 2 over 2. Wait, are you saying all of these points could also be represented as unit vectors? Because if we drew an arrow from the center to any of these points, that arrow is going to be how long? Always 1. Okay. So all of these coordinates on our unit circle are unit vectors. There are two that pop up quite a bit, and they get a special name. These are the unit vectors I and J. Okay, so that is a lowercase I, but instead of a dot, I put an arrow above it and a lowercase j. Same idea. These will always be lowercase when we do these. Don't draw me capital I's. It means something else. Lowercase I is the unit vector in the x direction. That is a j, yes. So this would be a unit vector that is 1 unit in pointing to the right. Lowercase j would be the unit vector in the y direction. This would have a length of 1 unit, and it would be pointing upwards. And this brings us to a fourth way that we can represent vectors using this ij notation or unit vector notation. Our vector v was 4, 3. Instead of writing it that way, I can write it as my unit vectors I and j, but both multiplied by a scalar. Anybody want to guess what number I would multiply the I by? 4. How about the j? Can you guys stop, please? Thanks. 3. Okay, and we'll talk graphically about what that means, but if you look at your little graph right here, if you imagine if we started at the origin and we went over 4 unit vectors in to the right, and then we went up 3 unit vectors, we would end up at B again, okay? And what we're going to learn when we start looking at these graphically is if you can start at the same point and end at the same point, you are looking at the same vector. Okay, it doesn't matter how you get from there to there, it is the same vector. So I can think about this as going over 4 and going up 3 as just 2 steps, or I could think of this as 7 steps. 1, 2, 3, 4, and 1, 2, 3. And there are an infinite number of other ways that we can get there, and we'll talk about that later on. For right now, see if you can write me the unit vector representation of vector W. Question? Yes, we definitely can define translations with vectors. That's an awesome connection. Good for you. Yeah. So it's taking you from one position to another position. So going from wedge notation or component form into this unit vector form is just a matter of sticking an I and a j after the x and y coordinates. Those are pretty simple. Say again. If the y coordinate had been negative, I would have put a minus here instead. If the y component, I should say component, not coordinate. So one of the traps, and I'm trying to be as careful as I can here, one of the traps as you start dealing with vectors is to start getting vectors and points confused, okay? So I'm doing my best, although I will make mistakes, and I'm sure you guys will too as you go through. I'm doing my best to talk about these as components and not coordinates. They can sometimes represent coordinates, but not always. So yes, if my y component had been negative, then I would put a minus here. Great question, thank you. Other questions? Yes. Yep. So we can represent position and coordinates with vectors, but the initial side must be at the origin. All right, questions before we move on? All right, so we're going to talk about making unit vectors. So our next task is going to be to create a new vector that's in the same direction as v, but I want it to be a unit vector. So I want it to be pointing the same direction of this, but if I were to measure it, it should be only 1 grid space long. and then we'll repeat it for W. So how do you think we go about this? What do you think? I love that. You're talking about just taking a small section of this whole thing? How much of this thing? Give me a ratio or a proportion of the whole thing. How much do we want to keep? Half of it? 1/4 for this? No, we're getting closer. 1/8? 1/5? Oh, 1/5 might make sense, because how long is this vector? We found the magnitude of it a moment ago. The magnitude is 5, right? So if we just portion this out into 5 little sections, just like you were saying, each of those little sections would be a unit vector, and they would be in the same thing. Well, how are we gonna go about getting 1/5 of a vector? We can just multiply it by a 5th, right? We are allowed to multiply a scalar. 1/5 is a scalar times our vector. Vector V had components 4 and 3. So our new vector that we're hoping is a unit vector would be 4/5, 3/5. I'd like you to prove to me and to yourself that that's a unit vector. Please find the magnitude of that vector. What are we hoping we come up with here, folks? If it's a unit vector, what does the magnitude need to be? It needs to be 1. So let's make sure it is. I'm going to have to do some... All right, so you do need to... I will not be providing you formulas for this unit. I do expect you to memorize the magnitude formula. That'll probably be the simplest one that you'll be memorizing, because you all know the Pythagorean theorem. Don't just copy my work. I want you to prove to yourself, not me to prove to you. I want you to prove to yourself. So do your own work. You're fully capable of doing this. You know how to square fractions. You know how to add fractions. You know how to take the square roots of fractions. Does it come out to 1? Oh, yeah. Nice. So our vector did come out to be a unit vector. So I'm put a box around it, because now I'm convinced that that is the correct answer to this question. In general, it looks like I need to pause for a moment. A few people are still getting this done. All right, as you're wrapping up here, I got a question for you. If I had a different vector, let's say, I don't know, vector A. And I found the magnitude of it. All right, that's the magnitude of vector A. This is the part where I want you to be like saying these things as you're writing them. You don't need to write this down. Just pay attention. See if you can answer my question. Actually, I'm just going to write it up here. My question for you, and I don't want anybody to shout out answers, just think about it. What is that? Say it to yourself, but in your head, and then see if you can phrase it in words, what we're doing here. Anybody want to put it into words for me? What did I just do to vector A? So I'm multiplying vector A by, can we all see this now that this is a scalar? Okay. So I have some news for you. We're going to explore this in more detail on Tuesday, but when we multiply a vector times a scalar, we're always going to get another vector. The size may change, but it will always be pointing in the same direction as the original one, or the opposite direction if we multiply it by a negative scalar. So when I do this, I'm creating a new vector that's in the same direction as vector A. And how big is my new vector? It is 1. It's a unit vector because I've divided it basically, or I've multiplied it by the reciprocal of the magnitude. What I'm doing is what we just did right here. We took the magnitude, which was 5. We multiplied by 1/5 times the vector. So this is the formula. This formula appears in your book. It may have it like this instead. This is the formula for finding a unit vector in the same direction as a vector. Okay? If you're a formula collector, feel free to memorize that. If you're more of a conceptual person, then we can just kind of think, oh, I'm just going to take my vector and multiply it by 1 over whatever its magnitude is. I'm shrinking it. When I multiply it by that 1/5, I'm shrinking it down to be a length of 1. All right? All right, here you go. Do this for W. You don't have to do the prove to yourself part, but find me a vector that's the same size, that's in the same direction as vector W, but is a unit vector. Find me a unit vector that's in the same direction as vector W. I'll give you a hint. You're going to take vector W, and you're going to shrink it down by multiplying it times something, some special number that we may or may not have already found. Vector W was -2, 2, right? What am I going to put down here? What am I going to put down there? 5? Now, if I put 5 down there, I'm cutting this into 5 equal pieces. Is that how long W was, though? You want to put 2 root 2 down here, huh? Because that is the magnitude of W. All right? We're basically dividing W by its magnitude. So it's not always going to be 5. It's always going to be the magnitude of whatever it was. Now, you'll be doing some of these problems in your book where you haven't already found the magnitude of this thing. So it will become a 2-step problem. You will first find the magnitude, and then you'll multiply it by the vector. Or not the magnitude times the vector, but rather the reciprocal of the magnitude times the vector. And if we do this, well, folks, again, please don't just copy my work here. You guys know how to multiply things with radicals, okay? Do your own work. Do your own work. And then check against mine. Yes. Ooh, what a great idea. I love that. For sure. Do you guys hear that? So if you are multiplying, so you're saying right from here. So if, as soon as you see this, you're like, oh man, I'm going to end up having to rationalize two fractions at the end of this thing. But wait, what if I rationalized it first? And then I wouldn't have to do it later on. So yes, that's a great idea. So the question was, could we have rationalized this first before we multiplied so we didn't have to rationalize it on the inside? Now this one happened to be the same thing, but they won't always. I think that's a great strategy. I love it. Mathematics is sometimes that fine line between laziness and efficiency. It would work, yes. Yes, you could rationalize this first. When you rationalize it, you're not changing the value of this scalar. You're just changing the way it looks, right? It's the same number, you just be multiplying a different version of it so that we didn't end up with two separate fractions that we had to rationalize later. Great question, thank you. Other questions about this one? Did anybody find the magnitude of this and make sure it was 1? Came out to 1? Awesome. All right, how about this one? Find a vector with a magnitude of 100 that's in the same direction as vector v. How do you suppose we do that? So we're going to find a new vector. We're going to find a new vector, and the magnitude of this vector is going to be 100. So how do we do that? I'll give you a hint. We're going to do something to, well, another vector. Question is, do we want to go all the way back to vector v for this, or is there something we've already done that might make this a little bit easier for us? We already found v, but as a unit vector, didn't we? This is a vector that's already in the same direction as v, but it has a length of what now? 1. Couldn't I just multiply this times 100 and that would get me there? That's it. So I would just multiply 100 times what we've already found. And let's label this. Please label what you're doing here. This was the unit vector in the direction of vector v. So let's see, 100 times 4/5. 4/5 of 100 would be 80. And 3/5 of 100 would be 60. And are we fairly confident that 80, 60 would have a magnitude of 100? Probably. But if we wanted to be sure, we could just do a little bit of work. Magnitude of 80, 60 would be the square root of 80 squared plus 60 squared. That's 6,400 plus 3,600, which is 10,000. And the square root of 10,000 is 100. So it works. All right, now, folks, on your assignment, you're going to get a problem where they're going to give you some vector, okay? So you don't need to write this down. I'm just making this up as I go along. They'll give you a vector and it'll be -7, 2. And they're going to say, find me a new vector that's in the same direction as this vector but has a magnitude of 25. So what's your process? Unitify it. I like that term. Unitify it. Unify it. So your first step is going to be to turn this into a unit vector. What are we going to need to find in order to do that? We'll need to find the magnitude of this first. And then we'll use the magnitude to find the unit vector that's in the same direction, and then we'll take that unit vector that we found that's in the same direction and we'll multiply it by whatever they want the length to be. All right, so we have not done a complete example of one of those from start to finish, but you have all of the pieces here in your notes. All right, and we can have a look at some of the assignment questions here in a minute. We're getting close to finished. Is there any questions on this? So this is where we start getting a little technical, is when we get into the magnitudes and then turning things into unit vectors. This is a key piece of this unit, okay? So this is the part I really want you focused on as you're working your assignment. Checking your answers. Show your steps as you're going. If it helps you to draw arrows and make some notes even on your assignments, then go ahead and do that. But you will be doing this over and over and over again. And on top of this, we're going to be adding some other complex operations that we're going to be doing. So if it helps you to, annotate as you go through the steps, write out in words, find the magnitude, and then show your work for finding the magnitude, and then write out in words. Turn it into a unit vector and show how you do that, and then write out in words, multiply the unit vector times the new magnitude. Okay? All right. Questions? How you guys feeling right now? Let's show me your thumb meter. Where are we at? All right, this is good. Honestly, at this point in the game, I'm expecting like kind of less than half full tank, okay? And that's okay. It's okay. You're going to practice this. Hopefully, we'll get you at least up to half a tank by Tuesday. And then Tuesday, we're going to wrap all this back. We're going to circle back on all this stuff again, but we'll be looking at it through a graphical format, which is going to just bring this all together. Okay, the last thing that we did, I saved this for last because it is something that you guys are going to just be awesome at. It is finding the direction angle of a vector. So before I give you the notes for this, I want to talk about what I mean by the direction angle. So, the direction angle for vector v would be this angle right here. It's going to be in somewhere between 30 and 45. I don't know exactly what it is. But it's acute. The direction angle for v is acute. How about the direction angle for vector w? Does anybody want to guess? Give me like a ballpark for this one. Between 0 and 180? I agree. 135 is correct. So we always measure from kind of that direction that's the positive x-axis, just like we were doing in our unit circle, right? So the direction angle for this would be that angle there. It's bigger than 90. It's less than 180. The fact that the x and the y components are both the same means that this little reference angle would be a 45-degree angle. So how are we going to find the direction of a vector? There's multiple ways to do it. You can use an inverse tangent. There's a formula involving inverse tangent. But then you also have to think about what quadrant it's in, like which direction it's going. So if you do the whole inverse tangent thing, remember inverse tangent will only give you answers between what two angles? Between negative 90 and 90. So inverse tangent would not work for this. So there is a formula for it. I'm not going to tell you the formula. It's in the book. You're welcome to copy it down. Here's the way I deal with it. I just draw a little sketch, all right? Let's find the angle for V. Draw me a little sketch of V and put let's go ahead and write down what V is here. I know you've got it in front of you, but it's 4, 3. And put the origin of V at the origin, so the starting, which it already was anyways. And then I'm not making this to scale or anything, but it goes in this direction. V points in that direction. And I know because of my components that if I were to drop a vertical line down right there, I would create a right triangle that has 4 and 3 as its two sides. And then put your theta in there and write a trig equation and solve for theta. Yeah, we're gonna find. Well, it's find the direction. Yeah, I'm covering up something that I don't want to show you just yet. I made a game time decision to hold that back from you until after we gone through this. I figured, like, let's go over let's do it the way that we all know how to do already, and then I'll give you the more complicated version of it. Okay? And so we're gonna come back and do this for vector W in a second. So. But we can write a trig equation for this. The tangent of theta equals 3 over 4. We weren't stuck with only using tangent because what did we also know about this? We already figured out that the magnitude was 5. So we could have used sine or cosine, but 3 and 4, those are pretty evident. So we'll do an inverse tangent on both sides and get theta equals the inverse tangent of 3 over 4. We'll grab our calculators, make sure we're in degree or radian mode, your choice. Typically vectors are worked in degrees, I think, at least at this level. So I'm going to go degree mode. A tan 2, yeah, that's the... It's about 36.9 degrees. Right, but you have to have two arguments. That's what the 2 is for, right? So, yeah, we were just talking about, there's anybody else here do any coding, have done coding? There's most coding languages will have a function called atan2. So atan is arctangent or inverse tangent. And atan2, instead of putting 3/4 into it, we would say atan2 of 3 and 4. And if you use that, based off of the positive and negatives, it will figure out what the actual thing is. It saves us a little bit of step. Don't worry about that just now. Are we okay with this 36.9 for this one? Can we go on and find the direction for vector W, please? Now, I'm not sketching vector W as it appears on your little half sheet here. Vector W has the components -2, 2. So when I sketch it, I'm going to make it start at the origin. So we're allowed to shift vectors around wherever we want to. So this would still be vector W. I just need to make sure that it's going 2 to the left and 2 up. Okay. That vector has the same direction and magnitude as the one that's on here. And then we'll go ahead and once again make ourselves a little right triangle. And I'm not messing around with positives and negatives. I'm just going to stick this 2 and this 2 on here. And I'm going to solve for this angle right here. Now, is this angle that I'm solving for the same angle that I want to as my vector? So we're going to need to eventually find theta. Theta is here. But first, we'll start by finding this angle. Let's call it, what do you want to call it? Alpha, X? I'm going to go alpha. I'm going to find this angle here, and then we'll use that to find theta. So again, it's a right triangle. We got opposite and adjacent, so we'll go tangent again. Is 2 over 2. Now, most of you probably already know that this is going to end up being 45, right? But let's go ahead and write out the steps because it won't always be 45. You guys know how to solve these. We've been doing that since geometry. We would do the inverse tangent of 2 over 2. Which comes out to be 45 degrees if I were to put it into my calculator. But remember, that's not theta. That's like a reference angle, but we know how to take a reference angle and find the actual angle. It's a matter of subtracting from 180 or Subtracting 180 or subtracting from 360, it just depends on where it is. So in this case, we would do 180 minus alpha, that would get us theta. So 180 minus 45 gets us 135. All right, there are several really fun, complicated formulas for finding the angle of a vector. If you look at the way the book does it, they set up an equation and they solve a trig equation to do it. For me, I've told you guys this before. I'd rather just connect it back to something that I already know how to do. So, and we know how to do this. The thing that I was hiding, any questions on this before I show you the thing I was hiding from you? So my original intention was to do it the way that the book did it, which is interesting. So this, you can write that down if you want, but I think most of us can probably look at that and I'm hoping that you can kind of look at that and see what's going on and maybe make a connection back to some trig stuff that we did in the last couple units.
Like the actual, like, because like in that quadrant, isn't the x is negative and the y is positive?
Yeah.
So you can kind of reason it out.
So we're thinking positives and negatives in quadrants. What else are you seeing here? What else are you connecting this to? So, yes, x and y values, and are we used to thinking x goes with which of our trig functions again? So the x component goes with cosine and the y component goes with sine. I'm hoping you made that connection. If I had just done the cosine theta and the sine theta without someone pronounced this thing that we're multiplying both of those by. What is that? The magnitude of vector b. If we took that away and we just had cosine comma sine, guys, please don't miss this. Shh. If we took that away and we just had cosine comma sine, we would be looking at a whole bunch of vectors. And again, we kind of talked about this. Those would be all of our unit vectors. The cosine and the sine would be our unit vectors. Those would be all of these things. Well, what if our vector isn't a unit vector? Well, we can just take the vector and multiply, or the unit vector and multiply it by a magnitude. So let's say the magnitude of v, well, let's not say it is. The magnitude of vector v is 5. If I found cosine of the angle and sine of the angle, then I could just multiply those two things times 5. The book finds the angle theta by taking one of these things and solving it. So the book does this by, they say that we know that this component for vector v was, what was it, 4? And we know that the magnitude is 5. So the book says, oh, then 5 times the cosine of theta is equal to 4. And then they solve that equation. All right. Except it's not always that. Sometimes you have to add or subtract from 180 or 360, right? So that's how the book will take you through it. There's some other ways to do it. I say you guys all know how to make reference triangles and reference angles and then find the actual angle. Do it that way instead. All right, let me get you the assignment here. It's on Canvas. I'll write it up on the screen. We're running out of time.